So starting with Project Bloodhound, which is not just another world landscape record. The aim of Bloodhound is about setting the ultimate record, going as fast as technology, current modern technology will allow us to go. That is, we initially set out to see if it was possible to go 50% faster than the speed of sound, Mach 1.5. Speed of sound being, is your first question? 330, 340. Well, and it does vary a little bit depending on. Yeah, absolutely. But let's assume it's air. Just take air as the example. Speed of sound in air depends with temperature. Absolutely right. In very simple terms, I'm talking to you, you hear me because all the molecules are vibrating, banging into each other, and the pressure wave I'm transmitting, you detect as a sound. If you heat the air up, molecules vibrate faster, they hit each other faster, the speed of sound goes up. If you go down, it's as simple as that. So, Mach 1.5, still air, you're looking at over 1,100 miles per hour. 400 and, what does that mean to the second? Public maths is always dangerous. That's 510 meters a second. We looked at that and said, that is not possible. All sorts of reasons. You'll get an idea of some of them later on. Limitations, we said, okay, 50% faster we can't do. How about 40%? Yeah, maybe with a bit of technology development. 40% has to be just over 1,000 miles an hour. So very quickly, by the time we actually need to convert that into a number that journalists can understand, it became an attempt to do 1,000 miles an hour. To create new science, to push back the boundaries, to make those sort of amazing videos you've seen on YouTube already, and actually to try and bring the science and technology of cars to life in a really exciting way. So that's the aim. This is the car that holds the current record. That was the car I was lucky enough to drive back in 1997. 763 miles an hour. That day it was quite cold, the speed of sound was quite low, so the speed of sound that day was about 750. So that's supersonic by enough to make it do what it says on the tin, the thrust supersonic car. Set that record 18 years ago, coming up for 19 years now. We still hold that record today, longest standing record in history. Get a car to go that fast on the ground, you've got some big technical challenges to overcome. What do you reckon they are? Yeah, friction. Friction from the air, friction from the ground, rolling resistance. You're going to have to overcome friction. What else? Yes? Yeah, absolutely. Lifting off is the big one. Running the car along the ground, it's huge. It's 4 meters wide and 17 meters long. You physically couldn't get it side to side in this space. It's longer than that. And it wouldn't stay here for long because it weighs 10 tons and go down through the floor very quickly. And being 4 meters wide, very pitch sensitive. 1 degree too much nose down at supersonic speeds, you would crush the front of the car into the desert with 10 tons of download. From my point of view as a driver, it's not a good thing. 1 degree too much nose up, it would generate 10 tons of lift at the front of the car. The front of the car would come off the ground very rapidly. It would get to an enormously high height. The engines would tear out with the loads of it going flat to supersonic airflow. The bodywork would come off, the chassis would collapse, and I would lose all further interest in that afternoon's proceedings. So keeping it on the ground absolutely is the big problem. Yeah, absolutely. You're going to have to put some power, not just some power, a lot of power to actually drive it through the very thick air down at ground level, as well as the roller resistance, etc., overcoming that friction. It's not just making the friction small, it's having enough power to get over what's left. Anything else? Yeah. Yeah, turbulence, actually controlling the loads. So that's part of keeping it on the ground, but it's also managing the turbulence, which is not only controlling the vehicle, but controlling the effect on each piece of the vehicle. Turbulence at the back end of high-speed jets, even high-speed cars, can smash the back end to bits, however strong you make it. The aerodynamic turbulence can destroy structures like that. Yep. The whole thermal control of everything from jet engines to wheel bearings to the vehicle itself. Plus, some idiot painted it black and then we ran it out in the desert, so it got really, really hot. Yeah. Keeping it in the straight line, it's not just controlling it that way, it's controlling it that way as well. You're exactly right, so that's all part of the aerodynamic control of not just turbulence, but the actual huge forces. Anybody else? Yeah, absolutely. This bit down here, where are you going to find somewhere large enough and flat enough to run a car at these sort of speeds? I'll give you the last one. Where are you going to find wheels that can rotate that quickly to survive those kind of loads? It's going to need to be a very special solution. There's no kind of rubber tyre that will survive those loads. I'll come back to that. The biggest single one, keeping it on the ground. Excellent. I'm going to show you a very short clip of video. We had some competition back in 1997 out in America where we set the supersonic record. And the Americans, this was the year before, 1996, the Americans ran a project, a short clip of BBC video. And you'll see at the end of it, the American car in the distance running in that direction on the horizon, filmed from several miles away. And as the car's running across the desert, they haven't got this aerodynamic balance right. They're not controlling the pitch. It doesn't lift off at the front, but it does build up shockwaves at the back and lift off the rear wheels. And the car then falls away from the camera, so instead of trying to pitch into the desert, as it falls over on its side, it then pitches towards you at 650 miles an hour. It turns through 90 degrees in 4 seconds. So this is the world's fastest car crash.
In the desert, the British team have a rival. American Craig Breedlove has won and lost the record 5 times. Now, 60 years old, he's determined to be the first man through the sound barrier. A year ago, he reached an unofficial 670 miles an hour, but then his car seemed to take off and careered wildly off course.
Oh no. Crash. Guys, go sideways.
Nearing the speed of sound, it's keeping the car on the ground that is the toughest challenge.
Hard right turn.
That is actually slightly worse than it looks. Not only did he not keep it on the ground, rolled the car over, he got very lucky, it fell back on its wheels. This is the crowd line. He's now the wrong side of the public, including a couple of local school buses. So he drove through the crowd line at 650 miles an hour, fortunately through a gap. That's very bad in motor racing. Okay, so that's a bit of evidence to say controlling the car, keeping it on the ground is a tricky bit. Now, traditional way to do that, the aerodynamic solution, finding out how to keep it on the ground, you put it in a wind tunnel. Why will this not work? Not fast enough where you can build a supersonic wind tunnel. They are very expensive, but it's technically possible. What can you not do in the wind tunnel? What can you not simulate? Yeah. You can't simulate the thrust. There are allowances for that. People building wind tunnels for aeroplanes. But you're right. It's difficult, but you can allow for that. There's another bit you can't do.
There's a lot of drag.
Yeah, drag, but force on the driver is a factor, but that's not a wind tunnel problem. Yes, absolutely. You can't make the ground go past. What we're trying to simulate is a car with the air going past supersonic and the ground going past supersonic as well. Now, if anybody thinks they can build a supersonic conveyor belt, do come and tell me how hard this one. This bit here, of course, this is what we're trying to do. Over the top, it's the same as an aeroplane. We know what happens there. People have been doing that for 50 years. It's underneath the car's throttle. So, early 1990s, there's a brand new technology, which you all take for granted now. 20 years ago, this was absolutely brand new. Computer modelling, computational fluid dynamics. Modelling all the airflow with a computer program that would predict where the airflow was and actually show you where the pressures are on the vehicle. And all different colours are different pressures. And that's brilliant, because you can add all those up and actually work out where that critical angle is to keep it on the ground. It's even better because the engineers can then add up the pressures to see what load each bit of the car takes, so they can now start to use it as a structural design tool. Fantastic bit of equipment. But this is a new science. It's been done by one of the biggest computers in the country, and it's the same computer that the UK Met Office is using to forecast the weather. Anybody see any problem with trusting the computer that does the weather forecast? Yes, we do. So we need to find a different way of testing this. So if you can't put a model in a wind tunnel, here's the bit of innovation that made all of this possible. Here's the bit of really clever thinking, and this, by the way, all of this process was done with Swansea University doing all of the modelling. It's very much with UK education right at the centre of it. If you can't put a model in a wind tunnel, how about taking a wind tunnel model into the outside world and firing it at supersonic speeds? to 800 miles an hour in just less than 1 second. So this has got two huge advantages over wind tunnel testing. First of all, this is a lot more fun than wind tunnel testing. But it's also an independent, real-world method of testing that computer model. We found out that this was giving really good data. This basically worked. We had validated this new research technique, this new theory, which then allowed us to build that car, knowing that we could keep it on the ground, and then allowed us to take it to supersonic speeds back in 1997. And you can see, looking over the car, it is travelling supersonic on the ground. You can actually see the shock waves being generated from the various different bits of the car. Which means these guys still today are the world champions. Still the fastest car on Earth by a long, long way. Hooray for us. Stop now, we hold the world land speed record. So the question is, why are we doing this? Spending a lot of somebody else's money in generating a vehicle that the world does not need. You know, nobody's ever going to do this, go to school at supersonic speeds or get to the shops at 1,000 miles an hour. It's not going to happen. This is not a device you're ever going to see being used on the roads. It's a technology demonstrator, yes, but so what? There's lots of other ways of doing that. Now there is some competition. There's the American car you saw crash in the video earlier. I wouldn't drive that personally, but it has been heavily re-engineered. The other end of the scale is another American car. They've taken a jet fighter and cut the wings off. You want to know why you can't run a jet fighter along the ground by cutting the wings off? Speak to these guys, they're having all sorts of problems. There's an Australian who's building a rocket car. He's talking about 1,000 miles an hour. I think that's as close as he's going to get to 1,000. But nonetheless, as you can see, it's a long way through completion. And then there's another design in the States which may or may not get built. There's a lot going on around the world. All of these people, their main aim in life is worrying about the land speed record. That's one of the things I wake up thinking about in the morning. The rest of the world that you're going to live in, has got some rather more serious problems that you need to solve. Like the fact you haven't got enough engineers to build it and run it. Right now in this country, we are training about half the engineers that you are going to need in 5 to 10 years' time. We are going to need in 5 to 10 years' time. But I intend to leave the problem to your generation to fix. And it's not just in the UK. It's European-wide. One of the greatest challenges facing Europe today. It's not even that bad, it's worse than that. UNESCO did the first ever global report on engineering and said there is a growing shortage worldwide, with the big problem being lack of young people. That's why we started building Bloodhound. We want to make the science and technology have a real wow factor. Hey, that's amazing, how does that work? For a bunch of kids who are going to be part of your generation in building and maintaining and living in that high technology, low carbon, energy efficient world, which is going to be your world. And that's only going to work with the right science and technical skills. We talked about what subjects you're doing. You're already there, but you're in a minority. You need more reasons to get excited about it. So that's the aim. We've put Bloodhound so far in front of 2 million UK students. Call it 2,100,000 because you guys are here now. And it's also going global. It's having more than just an effect in this country. Brazil is rolling it out across Brazil. There's a big education program in South Africa. Turkey's looking at translating to Turkish. It's having a massive international effect, as mentioned. And it's also got great gender balance, which I'll prove in just a second. Despite the fact this is about a car, and I have heard teachers say, that's all very well, what about the girls? Yeah, I'm sorry, engineering is for girls. You know, because the girls are at least as clever as the boys. I'm going to get punched from somebody in the front row, so not you. You know, the first F1 in schools Bloodhound rocket car competition we had, it was an all-girls school that won it. Because the girls were just that bit more careful and disciplined and managed to hold the wheels on straight, just like balloon car and faster. You know, the attention to detail does work. So that's what Bloodhound is trying to achieve. We also have got, we're launching next month, I think, the Schools Model Rocket Car Challenge. There's a series of model rocket car categories for Guinness World Records. There will be a national competition. If you don't take part in this, I'm going to be deeply disappointed having been here. And this summer there's going to be a national final. And I forget what the prize is, but it's up at the level of coming to see Bloodhound possibly in South Africa. It is worth putting an effort into this. Let me give you just a tiny flavour of the first school that did this a few years ago.
No reason why they shouldn't go back. Are we ready?
3, 2, 1.
tell you're having a good science, this is a science teacher, by the way. You can tell you're having a good science session with the science teacher who's jumping up and down with excitement. That was the first ever Guinness World Record for a model car, 88 miles an hour. Have a guess what it is now, the unlimited rocket class. 531 miles an hour. I reckon the first car to go supersonic called Bloodhound will be in a playground somewhere, whereas, it's a rocket. There are other classes, and there are some of them still down in the 40, 50 miles an hour, so you don't need to have a supersonic test track to do this. But it is great fun, as well as being, it's the next step up from balloon cars. This is actually quite challenging science to get it right, and it's good fun. So that's what we're trying to do. We're trying to actually create this as an education story. But of course, to do that, we need to build a car. So how are we going to build a car that goes 1,000 miles an hour? Well, first of all, we know this works. We did this best part of 20 years ago. Computational fluid dynamics, it's just the computers have got better. So now we can model hundreds of times more accurately and project an awful lot more. So we're not just getting the loads on the vehicle, we can now look at drag, turbulence, which is really complicated, to the point where there are different models, and we're actually going to validate some of that theory when we run the car. Most of the aerodynamic sensors in the car are at the back, because we're actually validating some of the science to prove which theory is more accurate. We can even look at the various different aspects of surface drag, aerodynamic drag. It's an amazing bit of kit. But even when we minimise all the drag, we need a lot of power. We've got the world's best military jet engine from Eurofighter Typhoon. X-development engine, the orange wiring is test harness wiring, so it's something the MOD isn't using anymore, so we're borrowing. This is land speed record recycling. But that's not enough. This aeroplane will not do 1,000 miles an hour close to the ground. It only goes to about 900, 920. We need to go faster than that. So we're adding an extra belt of power from the next generation of satellite launch technology. This is the stuff you're going to see launching satellites 5 to 10 years from now. Try again. 5 to 10 years from now. Hybrid rocket technology. Why hybrid? It's very controllable and it's very safe. Solid rubber fuel and hydrogen peroxide as the oxidizer. And literally, there's a catalyst pack here, layers and layers of silver oxide mesh. You force hydrogen peroxide, which chemically, I know there's some chemists in the room, chemically hydrogen peroxide is anybody? H2O2? Yeah, stuff it through the catalyst pack. It actually breaks the molecules to produce H2O plus O2, and the energy it releases means that mixture comes out at 600 centigrade. So we've now got oxygen-rich gas going down a tube full of rubber, 600 centigrade, it sets fire to it, which puts it up to between 2,500 and 3,000 degrees centigrade. So that flame is coming out at twice the temperature of molten lava, and generating all the thrust, because those the actual byproducts of that combustion are incredibly energetic, incredibly hot, and when they're directed out of the nozzle, they will produce, in this particular case, that's just going on for about 3 tons, about 30 kilonewtons of thrust. Put 2 or 3 of those together, makes a big difference. That's what makes the car. Just to pump the hydrogen peroxide into that, we've got to put a ton, a cubic meter through in 20 seconds at 76 bar. So we've got a 550 horsepower V8 Jaguar engine just to power the rocket pump. Gives you an idea of how powerful the pump needs to be. The wheels, I mentioned the wheels earlier. Design, manufacture and completion of the wheels, 6-year program. Because the wheels need to rotate 10,000 times a minute. The wheel rims are pulling 50,000 times the force of gravity outwards. Very high stress here, very high stress at the centre of the wheel, where it's literally trying to tear the wheel apart. That's why nothing like rubber will work. This is up at the limiting strength of the very best aerospace grade aluminium alloys. We actually had 4.5 tons of aluminium made for us, specifically to be able to cope with those kind of loads, and they actually then forged 18 discs to manufacture 4 sets of wheels and 2 as quality control. All this aerospace grade technology, why am I comfortable about doing this? It's being built to the same standards that aeroplane engines are. That's what I do as a day job. And we finish up with 3,500 bespoke components as a kit of parts, which we are now putting together with the world's fastest engineers. finished article. That's the first assembly of the whole vehicle. We completed that at the end of last year. Did anybody get up to Canary Wharf to actually come see the car on the public launch? You'd have had to be very quick. The whole event was a 2-day public event. It sold out in about half an hour. It was amazing. And that's where we are right now. Now spending the rest of this year actually getting this fully working. We've got pretty much all of the bits. We now need to get it running. The aim is to have it ready for testing back end of this year. Initially in the UK and then out to the desert next year. And remembering that it's not just about building the car, this is about telling a story. This is about bringing the science and technology to life. So if you haven't had a chance to sit through a lecture like this, it's about trying to find ways of putting some amazing numbers. 13.5 metre, 8-tonne vehicle, which is developing more than 180 Formula 1 cars in power, jet, hybrid rocket, the Jaguar V8 engine. The bit I still find slightly scary, I can't quite picture it, is from a standing start, being at the other end of a 12-mile track, stationary again, 2 minutes after setting off, having been through the middle kilometre in that distance in 2.2 seconds, 3.6 seconds for the mile if you prefer. That's actually what we're being measured on for the land speed record. Just these numbers that excite me. And it's about turning this story into a real story. Now, traditionally, one of the ways to do that, a simple way, is to build a full-scale mock-up and then show people in context it's going to look like this, which we did in London a few years ago. It's London Street taxis, it's half the way to the double-decker bus, etc. Nice quiet Sunday morning in London. Turns out it's illegal to take heavy goods vehicles into central London on a Sunday. We now know. But the press loved this, as you can imagine. Made all the daily papers, page 2 of the Times, huge picture, big article about this car, science and technology, 1,000 miles an hour, great. How many of you actually read the Times? If anybody says yes, I won't believe them. The whole point is, target audience is actually about 10 years old, and she doesn't read the Times. So we need to find other ways to bring this to life. Bring on things like YouTube.
London SSC engine start. Engine winds up, LA response, LL response. The most sophisticated land speed record car in history. Bloodhound supersonic car with the engine now winding up, ready to go. Hydrometers starting to come up. Power generators online. Power systems are online. Stage 2. Cascade. Still fail.
is that? or not, as the case may be. Actually, none of you would have seen that on YouTube. I actually pitched that from Coventry Motor Museum. That's the Bloodhound simulator that they've just started running. Again, if you ever get a chance to drop into Coventry, they've got previous cars there as well, and the what they call a 4D simulator. There's no such thing as 4D, just bear with them, it's a good simulator. But the point, 15 million viewers on YouTube, on our YouTube channels so far, for a car that hasn't even been finished and started running yet, that's got to say we're doing something right. Getting that message out there is working, and hopefully after today you'll have a chance to go look at it. You've definitely got to enter the rocket car competition. Like I said, it's good fun. It's about making science fun at all levels. We also mentioned one of the big challenges, in fact I think you've mentioned the big challenges of which desert you run. And we searched all over the world for a place that was going to be at least 12 miles long, perfectly flat, needs to be dry for several months of the year, but ideally would flood once a year to make it, to re-level the surface and make it flat. Because if it spends too long, if it spends years and years dry, you get dust blowing in, you get sand dunes, it's no good as a racing surface. So we're looking for those what's called endorheic lakes which, like the Dead Sea, fill up and gradually they silt up. And it's a very salt-laden environment. Like the Dead Sea, you'll eventually finish up with a dry salt flat. Bonneville salt flats being the most famous. If it's not quite so salty, you finish up with the mud actually drying out. It's a mud surface, which is actually a much better surface for us. It's more consistent, it gives the wheel better grip. So we're looking for ideally a mud flat. We looked all over the world using, again, Swansea University with satellite search technology, and found the best surface anywhere in the world. There were two of them in South Africa. The one that was just long enough and could be cleaned up was Haxine Pan, right in the Northern Cape. The downside with the surface is there's a lot of stones on it. Something like 16,000 tonnes of stones needed scraping off by hand. So they had a team, for the last 7 years, they've had a team of 300 people working every dry season to remove that from 20 million square metres. Now, if you start clearing a 10 metre wide strip, which is basically 3 lanes of the motorway, if you started from here and went to Dover, went through the tunnel, sweeping your 10 metre wide strip with this many people, that distance would take you to Moscow by the time you cleared 20 million square metres. This in itself is a world record. We're actually getting them a record certificate for prepping the best surface in the world, because they have left us with the best hand-prepared racing surface in history, as well as being the largest, which is the good news. And of course, this is also the place where we're going to tell the Bloodhound story live. So the other key bit of the car that nobody's done before, using the fact we are the first racing car, landscape record car of the digital age, the internet age, is we're going to use, we're actually going to use mobile phone masts to take live video and live data from the car and transmit it onto the internet. So wherever you are in the world, you will be able to watch the car run, you will actually be able to look at the data. Interestingly, because we'll be busy running the car, you get to analyse the data even before our engineering team does, because they'll be busy running it, and 3 hours later when they put the car back in the garage, they'll then start digging through the data to see what happened. So this is an engineering experiment that everybody, including you, can join in by watching it live, watching the video, downloading the data. Whatever you're interested in, whether it be the temperatures, the thermodynamics, the drag, the wheel bearings, everything. There's 500 sensors in the car, but a lot of data to plan through. And the tricky bit is I can't tell you what it's going to look like, because we don't know. And no one has ever been this fast. Current record, as I said at the start, 763. We're putting 250 miles an hour on that record, because 1,000 is the average 2 ways through the measured mile to do this. We'll actually be topping out at 250 miles an hour faster than the previous record. We didn't expect to see shockwaves off the previous car. We didn't expect an awful lot of other things. But whatever we see, the whole point is you get to watch it as well. That's the exciting bit. All I can do by way of saying you might see this is at least look at what happened last time and show you a couple of the effects that we had. First of all, the fact that we actually saw shockwaves on the surface, because the disturbance of the air, that sudden shock change in pressure as a vehicle arrives faster than its own bow wave and makes a sudden spike in the pressure of the air around it, is what causes a shock change in pressure, and there's a shock wave. And you can actually hear that when it passes your ear. If you're standing still and it goes past, you can see the sound. That shock wave causes the sonic boom, because it's a sudden spike in pressure, your ear hears it go out back. That's what causes it. You can see it when you're running on a dusty surface because the shock change in pressure disturbs the dust on the surface and the sun changes the colour of the surface. And I'll close by showing you a little bit of video of that. And this video will show you two things. One of which is to prove that the world is round. Everybody, first of all, let's just check. Everybody here agrees the world is round. Excellent. Does anybody reckon they can prove it? Go on. I've heard some great answers this way.
We use a technique that the ancients very big astronomers used, which was to take 2 points of the world.
Yeah.
And you measure the shadow, one at the equinox and one away from it, and change the angle of the shadow with
Yeah, absolutely. And you do some complex trigonometry, but you have to make an assumption about how far away the sun is. So you can measure either the curvature of the Earth or the distance of the sun, but it's quite difficult to measure both. You have to assume one to get the other. But the principle is exactly right. However, here's a much simpler way of doing it. Take a completely flat surface, which is a 12-mile, 14-mile long dry lake bed in the US. Except, of course, because it's water laid, it is laid to the, it's an isogravitic surface. It's flat to gravity. Because the world is actually round, the surface is not flat. The surface is actually curved. It's actually part of the globe on which we sit. So the car is actually about 6 or 7 miles away from the camera at the moment, and it's here. This is the dust trail behind it. The reason you can't see it is because it's physically hidden behind the curve of the Earth. And you're about to watch it drive up over the curve of the Earth for the first time in history, travelling faster than its own sound. Fast. Just wait to see what we can start doing next year. This is about not just a new land speed record. Like I said, we already hold that. Hopefully the Americans and the Australians will actually take the record from us over the next year, because that would be great. It's so much nicer to take it back off them rather than break our own. This is about developing the technology to push back the boundaries of physics as far as it's possible to go with modern technology. And also to share all of that while we're doing it, which is why you can see all of the design drawings of the car on our website now, where you can see a lot of the animations of what we're expecting to see now, and why we'll be running live video and live data from the car as we do it over the next 2 years. And also giving you guys a chance to do things like everything from studying the various Bloodhound lesson plans at whatever level you're doing science and technology, all the way through to the fun bits of doing model rocket car challenges. And if you do win, we'll see you down at Bristol where we're building the car. That's pretty much all I've got to say. It's about the science and technology and bringing it to life and making it fun, but it's also about whatever interests you guys. So, floor's over to you. Questions?